Have you
This is
mentioned?
what.
This is
So
the key word.
this is what was mentioned in the slide. So
Uh-huh. So it involves the measurement of the charges. And you have to apply some fixed potential. Have you mentioned this one? The fixed potential. No, it's not there, right? To find out the optimum potential. No, you have to mention here. This is the very important keyword for a chronocoulometry, that you are applying a very fixed potential. Generally, from the cyclic voltammetry, these things that I already described many times. When chronocoulometry or chronoamperometry, they are, you have to mention that you are applying a fixed potential, and then you are getting charge versus time. Okay, Tharmai.
okay, okay, sir.
And so this point is missing. This is very important point. Okay, then go next. Yeah, point of view. This is the very, I think, very simple things. I think it is almost right. I gave the almost full marks here.
Okay,
Let's
sir.
go. So let's say I cut something little bit marks. They're like this. You didn't mention the pitch potential. That's why I cut the marks from here. And
Okay.
number three, the interfering species can increase the background current, and if it is, what do you wrote? If it is
Con- conductive.
in nature, or decrease the, see, interfering species like the ascorbic acid, uric acid that I mentioned, like, or oxygen.
Yes.
So
Yes, sir.
what they are doing, so they can also oxidize. So why they are increasing the background, that you have to mention, because they are oxidizing in that applied potential, that you have to mention. Because of oxidation, you are getting the higher current, so you have to put the reason why.
Okay.
And you mentioned that is very good, that you can remove it by washing or adding by BSA. That is fine.
Yes. Okay.
Okay. So some actually I deduct some mark because of some very. If you have this keyword, then I am giving the full marks. So sometime I saw you don't have that very important keyword. That's why I deduct some mark. Otherwise, I given the 17, 18, almost 19, 20 also I given. So many students got 19, 20 also.
Okay.
Okay, let's go next. Yeah, these things, this is the important for the nanobiomaterial. So it is fine that you increase the surface to noise ratio. Okay, so,
Yes.
and also you have to draw some actual biosensor based on some nanomaterial. So you put just one sensor surface, but I asked just draw some design some biosensor based on some nanomaterial. You can design some actual biosensor here. Otherwise, I didn't cut the full marks here. I given here around 1.5 marks I given here. Not
Okay.
because you draw something, but you have to draw some actual biosensor, full biosensor based on some nanomaterials. Okay.
Okay. So you mean that the avenine, biotin, and then the gold nanoparticles like that?
Yeah, yeah, you have to
Okay.
clarify in the picture why nanomaterial is more important, right? The full
Okay.
maybe one reaction you can show there by the help of some nanomaterial.
Maybe I have shown in below, like I have shown this reaction.
No, here actually not full reaction here. See, this is the gold PCB. This is not nanomaterial. This is the plate. Printed circuit board is just kind of plate, right? It is not like a nanomaterial. Then you have to put some nanomaterial on the gold PCB, like graphene or some fullerene or graphene oxide or carbon nanotube. You have to put on the surface. Okay.
So like you had said that actually this plate is not of some metals, so we put some nanoparticles so that it becomes more conducting in order
Yeah,
to increase the signal to background ratio.
yeah. Gold PCB is something like the coated some plate kind of thing. There is no nanomaterial, right?
Okay.
Right. This is not nanomaterial. PC means printed circuit board. It is kind of the coated board, like gold gold, sorry, gold plated, not gold nanomaterial. So you have to put some nanomaterial here. Like, even you can put some gold nanoparticle here. Then you can put this antibody assays. It will bind on the surface. It is fine. But
Okay.
your concept is good. You are getting, but some point is missing. That's why you are getting little bit less mark.
Okay, sir.
Okay. Yeah. Go next. Go
Yes.
next. Go next. Yeah. So these things you described why point by point the RCT value why decreasing, right?
Yes, sir.
No, sorry. Let's go next. Limit of detection now you put there. Yeah, it's fine. Go down. Yeah, then you put this. So this is the actual. Your answer is almost correct, but if there is some missing like this keyword I told you, that's why I
Yes,
can't
sir.
reduce mark. So please improve the
Okay.
next class test like this. So at
Yes.
least the main keyword you should include. Then you will get the full marks. If you get
Okay,
the,
sir.
if you understand the concept, then I am giving the full marks.
Okay, sir.
Okay.
Yes.
Okay. Okay. Fine.
Thank you, sir.
Okay. Thank you. So please stop sharing. Then I will share my slide. Yeah.
Yes.
Okay. Uh, so can you share? Can you see my slide now?
Yes, sir.
Very good. Okay. So just I'm giving you some idea again because it was very informative class I taken last time. So I hope all of you are here who are present in the last class, and I hope you should not miss few classes because it's very important to understand the basic signal amplifications. So I can say so one thing here. So in my class, I saw some of you actually not turn in although during the exam. So all of you, I can ask you. So are you all of you are present during the class test here within 33 students here today? So you have written your class test everything. So all are you present last time? Can
Yes,
you
sir. Yes,
see?
sir.
Yes, sir.
So okay, next
Sir,
time I can send you an email. Some of you are absent actually. I saw.
sir, this is Ashwat.
Hello.
Sir, I had mailed you about my problem.
Oh, Shastad, yeah, I saw your email. Right. So you are absent, right?
Yes, sir. Sir, what happened was my Microsoft team did not allow me to join the meeting. Every time I tried, it gave me the same error message. I
Okay.
could see the question, but I could not join the meeting. So that
Yeah,
is
yeah.
why.
I saw your message. Just I wanted to discuss here. That's why I didn't answer. So one thing you can do, Shashwat. So please write the answer. Maybe hopefully by tomorrow, day after tomorrow, if possible. Don't take long
No,
time.
sir, I have given test.
So
So
you
the
have given
thing
it.
was, I have given the test. I could not join the meeting.
Okay, okay, that's fine. That's fine. I'm telling some of you are not. Some of you are not. I think I didn't receive any answers from you. Some of you. So please email me who are absent, fully absent in this test. Otherwise, you will be failed in this class test, right? So then you will get the bad grade. So I don't want to give you the bad grade, basically. So please improve yourself. You should cooperate also with me. So you have some WhatsApp group. Please let them know whoever absent. They should contact me immediately. Otherwise, maybe they will get 0 marks, right? That is not good for their final grading. Okay, so please let them know. Okay, guys. So just let them know if anyone absent, please contact me. Or I can send one email finally who are absent. Okay, so let's start now. The first things I can ask you, is anything not clear to you? That's redox cycling signal amplification. You can see this slide. I can repeat otherwise. Is everything fine? This slide?
Sir,
Uh,
a small doubt I was having.
okay, tell me which one.
Sir, actually, in the previous class, you were telling about the starting material. I mean to say that you were telling that in some case here our starting material was S, then R, then P, something
Hmm.
like that.
Hmm.
So then the confusion was that how to distinguish that starting material in case of whether it is NN or ECC or something kind of reaction.
See, this reaction actually
Voice
you
crack
need design.
info.
Hello.
Yes or no? I have my doubt.
Okay. See, first of all, you are designing your biosensor, right? So this is not like unknown sensor. This is you are designing. So if you are designing some enzymatic or maybe non-enzymatic biosensor, so you know very well which one you are designing. And starting material means, see, okay, let's open a slide. Let's open a new slide then. Okay, so this is a whiteboard. So let's explain it. So something like this is your sensor surface. So this is the actual sensor now I'm designing. Yeah? So this is your primary antibody coated your surface. Okay, this is the sensor ready for the signal amplification. So how you can amplify it? So you are using, suppose, a secondary antibody that labeled, right? That labeled with some label means I am putting L. So if you have some target like here, then this secondary antibody will bind, that is already labeled, right? So I remove this one. Now starting material means when you have to add from outside some reagent for signal amplification on the, so suppose this is a sensor tube, right? So you have solution here. So because I told you, so this is kind of the solution reaction, not the solid state. This is the solution state reaction, right? So you have some sample maybe, or maybe buffer. So you are adding some sample, right? Sample. The sample means liquid that you have to, this is some liquid sample you are adding on the biosensor surface. So on this sample, you have to, inside this sample, you have to add some chemical. So this chemical is your starting material or starting whatever I said, right? Starting material or starting reagent. Okay, Bhupendra, right? Bhupendra?
Yes, sir. Yes, sir.
So this is the starting material you are adding, that chemical. So what kind of starting material or chemical you should add? So if you want to add some like ECC redox cycling, right? I'm going the final one. Electrochemical, chemical redox cycling you are going to use. So what do you have to add? So you have to add some substrate first, right? That substrate will form a product that is something like say it is Q, not, so suppose this is, I cannot remember, suppose I am saying A. Okay, now this A, so will goes to B. See, so here starting reagent is, so you have to add from outside S, because S will react with the label and from the product A. Now see, here maybe here you can use P and Q. So this A will react with the P, will form the Q, right? And this Q now on the electrode surface, I mean this surface, this is the surface. This surface, it will release the electron, I mean it will be oxidized, right? So see, in this case, P, so P also you are not adding. P, are you adding P or no? No, you are adding P here, right? So you are adding S form the A, but you need any P is not here, right? P should react with A. So this one also should be added from outside. So this one also will be your starting reagent. So P will react with A, will form the Q, and when you apply some potential, this Q will be oxidized, will release the electron. Okay, Bhupendra?
Yes.
So this P will be your starting. Starting means you have to add some mixture. So here, what is the mixture? S plus P plus again something come. Now see, so B should go back to A, right? So that the cycling will be completed. So you have to add some again, some, as I said, this you have to add some reducing agent like T shape, right? Then it will form the T shape like oxidized product. So then this is also you are going to add from the outside. So AS plus P plus T shape. So this mixture will be your starting reagent. So this mixture actually you have to add just in the solution. Sorry. This mixture you have to add in the solution, then you have to wait for 10 minutes. Like this, 10 minutes or 5 minutes, whatever. Why we need this 10 minutes? Because of this reaction. So this one chemical reaction, this one chemical reaction, and here is the electrochemical reaction. That's why it is called electrochemical, chemical, ECC redox cycling, right? Redox. Why cycling? Because this, you can see here cycling, here cycling. This cycling should be completed. Clear, Bhupendra, now?
Yes, sir. Yes, sir. Clear.
Ask me again and again. No problem. No problem.
Okay.
So see, so like this way, I just taught you last class. Like this is the ECC redox cycling. So in the exam, I can ask you, From right now, I am just Tanmay, just see like this. In actually exam, I am just giving you this kind of questions. So if you attend my class every day, I think you will get the very good marks. See the ECC like this. I will give you the question from the today. I can tell you. So I can ask you what is the definition of the ECC redox cycling and design a biosensor based on ECC redox cycling and mentioning the starting reagent. Like this, just Bhuvendra asked the question. Same question I can give you. I just wanted to see your answer. So if you have this all the keywords like how I am explaining today in the class, if you say this all the keywords, you will get the good mark, full marks. So you have to mention what is the definition of the ECC redox cycling. So it should contain some electrochemical, chemical, and chemical reaction. So if you cannot remember like all the reagent name, so you can put like this way that I draw. Right? I also cannot remember this seriously. So how I am teaching you? I am just teaching you A, B, C, D, P, Q like this way. So same thing. If you understand the mechanism, you just draw it. A, B, C, D, P, Q like this, and just tell us what is the starting reagent, where is the electrochemical reaction, where is the chemical reaction, like this way. Then you will get the full marks. Okay, and these things I think I already told you that this is the actually full biosensor, right? Based on the electrochemical, chemical redox cycling. So I can tell you again. In NP is the nitrophenol here. NP you can see. So nitrophenol is the not much reactive on the I2 electrode surface. That's why we choose this material. So why we choose this kind of starting material or this kind of chemical? Because they are not much reactive on the sensor surface. Why we need this kind of material? Because we will get low. Why we need this kind of material? And that is not much reactive on the electrode surface. Why? Students, why?
Low noise, low background.
Low noise, right? Low noise or low background, yeah. So NP should not react very fast on the surface. So first of the main funda thing is that starting material should not react very fast on the electrode surface. That's all, right? So NP starting material, it should not react, right? Here Fc plus is the starting material, right? And sodium borohydride is the starting material. This mixture, see NP is producing AP and AP reacting with Fc plus and producing Fc0, and Fc0 actually oxidizing on the surface and generating the electron. So this one starting reagent, NP starting reagent, NaBH starting reagent. So first of things, so NP plus sodium borohydride, NaBH4 plus Fc plus. So these three are starting reagent. So first fundamental things you have to know, they should not to react each other also. In NP and NaBH4, they should not react to each other. Otherwise, they will release the electron. That electron can pass through the electrode surface. You will get the high current. So they should not self-reaction also should not be possible, or should very, very low. You can't say maybe totally 100% they cannot react, but they can react, but should be very, very low. First thing. And second thing, each one, when finally we will apply some potential like 0.3 volt, so that during that potential application, this starting material also should not generate any electron on the surface, right? If NP itself, they should not react on the surface. Sodium borohydride itself should not much react on the surface. Fc plus should not react on the surface, something like this. Because why? Because if you don't have any target, like 0, right? Like if you don't have any target, this one no, it means 0. If it is 0, you can see then there is no AP. So if there is no AP, no QI, right? If this is not, then no FC, right? Guys, clear?
Yes, sir.
So it means FC, NP, and sodium borohydride will be there only. And if they should not react to each other, so basically your background, it is the background of this biosensor. So I will ask this kind of question in the exam. What is the background in this biosensor? And who are the responsible for the background current? Okay, who are the responsible for the background current? So who are the responsible here? NP, NaBH4 and Fc plus, right? Right, guys?
Hello, sir.
Tell me.
Yeah, sir. How Fc plus is starting material? Sir, please tell him.
See, why the Fc plus? See, if you not add Fc plus, then it will be a EC redox cycling, not ECC. First of all, see, go back. Okay. See, in the EC redox cycling case, we are adding only substrate and R, one kind of reducing agent, right? We are not adding ferrocene plus. So what will happen? S will produce the P, and P can be oxidized on the surface. When you apply some potential, it will generate Q, and that will be reduced by R. Right? Then only one cycle. Means you can see here. So this one chemical, and this one electrochemical, right? So you can see this is the EC redox cycling. But if you add one extra chemical, that can take part in another cycling with this cycling. See, like the Fc plus. So if I add, suppose, see, O1 is the Fc plus, right? So if the O1 I add, then this O1 is the higher oxidation state, right? So this one react with the P, see, and it will form the R. So if you don't add this one, then this cycle will not be there. So one cycle will be less. Okay. So if you want to get the ECC, then you have to add one more extra chemical, or one more extra, we are saying this one, extra redox moiety we are adding. Means one, like Fc plus, it is the kind of one of the part of the redox couple, so we can add. So they can take part in the cycling reaction. Then only you will get one more cycling. See, here only chemical reaction, and then you have to add some electrochemical reaction, right? Just electrochemical reaction you have to apply, then you will get some. So then it will be EC redox cycling. But if you add Fc, then it will be ECC. Clear?
Yes, sir. Clear, sir.
You can add one more. So if you add one more, then you can increase the number of cycling again. But generally, it is enough to generate the very high signal to background ratio. It is enough. But if you add the one more, like A plus, maybe it can again, maybe one more cycle it will be done. Then on the electrode surface it can be generated. Then it will be ECCCC like this. Okay, clear?
Sir, actually, chemical reaction, if increase, then the signal is high.
Yeah, as I told you last time. Why?
Okay,
because this chemical reaction, actually, when this kind of cycling reaction, actually they are helping to transfer the electron much faster. The kinetics become much faster. That's why you are getting high signal. More cycle, the transfer rate will be much higher.
Actually, sir, reaction are occur in same time or individually?
See, you are actually giving the 10-minute incubation that I said, right? So that incubation time, so if you go back again, see here, actually all the chemical reaction will happen within 10 minutes. So within 10 minutes, so this stage will be done. So we will be waiting for only apply the potential, right? So when you apply the potential, this potential application actually will connect this full cycling on the surface, sensor surface, basically. Okay, so tell me.
But sir, this method takes much time, sir.
See, that's why I'm saying you have to choose such kind of the chemical that is not so slow. So if you choose some chemical, they are reacting. See, as I said, the NP is should not be reactive. That is fine. Now you are generating some product AP, and you already added FC. So FC and AP, see, these reactions should be fast. Okay. Now clear, right? These reactions should be fast. So if they are reacting slow, then your signal to background ratio will not that much increase. Here.
Okay.
Here.
Uh,
So you have to choose such kind of chemical. So as a starting material, they will be slow, but when you generate some product, so they will react among them very fast. So that's why choosing the chemical like this, we need many optimization steps. So one by one we have to check. They are reacting slow or fast. So if you check that within 10 minutes also they are not reacting, so you have to think about some other starting material, not NP, something else. So that is actually fully research purpose. We have to. So if you can design some new like this a new cycle within some starting material, then only that within that also you can get a good paper.
oh, okay, sir. I got.
So yeah, choosing this kind of chemical and getting very good signal to background ratio itself is a good research. People are trying to get very good chemical. How we need many optimization, right? So we need they should react slow, they should react fast. Then we have to check signal to background ratio one by one we have to check. So itself it is a research. Okay. So
Okay.
we already have some chemical that I am teaching you, but if you can discover some new chemical, then you can get a good paper. Okay. So this is kind of project you can do. If you want some new project, so this kind of project you can plan also. Okay.
Okay, sir.
Yeah. So when you be the final year project student, so you can think about something, some new biosensor design. If you succeed, then you can get a good one. I mean, good paper or something. Your thesis also will be much better than other. Okay. So this thing I already taught last class. Again, I am just stretching. Now, some another sensor. See, here I am going to tell you some another chemical. Basically, I am changing the chemical. See, here I put the nitrophenol. Here I put the APP. This is aminophenyl phosphate. This is one chemical name. This is aminophenyl phosphate. So this phosphate, this reaction on the electrode surface is very slow. And ALP, this is kind of enzyme. This is called alkaline phosphate. So this alkaline mute yourself, lots of background. Who are not talking, please mute yourself. See, so ALP, this is a kind of enzyme. They are very much specific to some substrate. So here the substrate is APP. APP is the reagent name. It is called aminophenyl phosphate. So it will react specifically with ALP. ALP is the alkaline phosphate on enzyme. So your secondary antibody that labeled with this enzyme. Okay. Now, if you don't have any target, so here in this biosensor you can see CTNI. This is cardiac troponin I. This is kind of a cardiac biomarker that causes the heart disease. So if you develop a biosensor for cardiac biomarker, cardiac troponin I, so you can design something like this. Your primary antibody coated on the surface with avidin, biodin. Now, if you have biomarker cardiac troponin I, and you can add a secondary antibody that labeled with alkaline phosphate. Now see, if you don't have this target, this is absent, then ALP will not be there, right? As there is no target, no ALP. ALP cannot bind because ALP already conjugated with secondary antibody. Now, if there is no ALP, then APP cannot react and form the AP. AP is the aminophenol. Aminophenol. So something like this, the same structure. This one, AP, aminophenol. So APP react with ALP and produce the AP. So if there is no ALP, so this full cycling reaction will be stopped. There is no cyclic reaction. So you will get basically background. So what is the background? Cause APP, and you need this reducing agent, right? Why you need reducing agent? Because AP will react with the another redox. I mean, one part of the redox couple, that is the ruthenium. This name is called ruthenium hexamine. And here ruthenium is the third oxidation state, +3. Yeah, ruthenium is the +3 oxidation state. Generally, we are using as a starting material in the ECC redox cycling the higher oxidation state material. You can see last time you can see Fc plus and Fc, we are using the +1 higher oxidation state. Same way here we are using ruthenium, another redox couple. Ruthenium 3, ruthenium 2 is another redox couple, but we are using 3,1, I mean higher one. Why? Because a higher one will be reduced by this material AP that can be generated from the substrate. So this one will react with 3 and form the higher oxidation state Q, and itself ruthenium 3 will be reduced to ruthenium 2. You can see. Okay, so generally in the ECC redox cycling, we are using the electron mediator that is higher oxidation state. Clear? Why we are using higher oxidation state, guys?
Yes, sir. Yes, sir.
So you can see the last one here we are using Fc plus. Here we are using ruthenium 3, like this. So this is the another couple, some reagent. Actually, we discover. So that's why I'm just teaching you here. So ruthenium 3 will react with the AP. But if you don't have AP, means in the zero target case, AP cannot form AP. So ruthenium 3 will be there only, right? As I said, ruthenium 3 will not react on the surface very fast because it is the starting material, ruthenium 3. So ruthenium 3, APP, and T-shape. So number 1, number 2, and number 3. So these 3 is the starting material, and one by one, when we apply some potential finally, like 0.3 volt, that time, so they also individually they can react on the surface. So ruthenium 3 individually, if they react on the surface, it will not generate much electron. APP, if they individually react on the surface, they will not react much electron. They will not transfer the electron. The T-shape also, if they individually react on the surface, they will not generate much electron. So basically, you will get very low background. But if this cycle actually, if you can perform this cycling reaction on the surface, you can see this ruthenium 3 can be converted to ruthenium 2, and these two will be oxidized again on the surface to ruthenium 3 when you apply some potential, and you are getting the electron. That electron you will measure by chronoamperometry or by chronocoulometry. Okay. So generally, this kind of ECC redox cycling case, we will measure the amperometric method, like chronoamperometry or chronocoulometry. These two methods commonly used in the case of redox cycling based biosensor. Okay, now next go then. Okay, so here actually I shown the what is the T-shape structure, but you know, I know to remember this one. This is the structure of the T-shape. Okay, now I will ask you some question here. See, in this case biosensor. So how we can design some new biosensor? See, in this case, see, we use FC, right? NP, sodium borohydride. Okay. And this case, see, FC, AP, sodium borohydride, NP, everything same. Right? Can you see this one? Right? All the chemicals same, right? So that is the things when you are going to develop some your own project during your maybe your 4th semester, if you want to develop some biosensor project. So you can think about how we can design a new biosensor. Some biosensor may be already reported, right? Some already paper already came. So how we can bring some novelty? Maybe this paper, just think, someone like Vibhuti already published this paper. Okay. Now, what's the name? Tell me someone name who want to work on the biosensor. Anyone here want to work on the biosensor? Maybe in your final project. Anyone? No? Or can you? Okay, just. Okay, so maybe like Bhavesh. So Bhavesh, are you there, Bhavesh? Hello?
Yes, sir.
Yeah. See, think, I am asking you some questions. See. Suppose Vibhuti already published this paper. Suppose this work already done. Okay. Now, if I ask you, based on this sensor, please design something new so that you can get some new work. Right? So, how you can design? So, what you can do, you can keep all the reagents same to minimize your time. So, you can keep all the reagent maybe same. So, these things like AP, NP, this reagent, maybe you just want to use your your seniors maybe already done some work. So, you want to borrow the concept from him or her. So, maybe you can borrow like FC, AP, NP, you want to use the same thing. But you have to modify the surface so that you can bring some novelty. So how will you modify? See here. Here reaction same, but what is the change? Can you tell me? What change done here in this biosensor and this biosensor? See this biosensor. Now see this biosensor. What's the change?
Sir, here we are changing the particular secondary body.
Yeah. Yeah. See, one thing you can see the change. Here we use the only gold nanoparticle. Right?
Yes, sir.
Second antibody. Here we see Ap3O4 gold nanoparticle. Like here we use a composite of the gold nanoparticle. Right? Okay.
Yes, sir.
Here gold nanoparticle. Here a composite of nanoparticle.
Sir, hello, sir.
Yeah, tell me.
Sir, please make the slide in the full screen mode.
Okay, yeah. Because I'm just changing the slide, that's why. Okay. See? Okay, so it is composite, right? Now fine? Slide is fine?
Yes, sir. Yes, sir.
See the one thing. This is the, uniqueness. This is the very, you can say the positive part of the nanoparticle. So if you can make some other kind of things, like some alloy kind of things, or some like some mixture kind of things, so their property will be changed. They can behave something different way. So only gold, maybe they, in this case, signal to background ratio, and if you make some composite, like this, so in this case, signal to background ratio will be much higher. So you can generate much, you can generate, and that biosensor will be more ultra sensitive than previous one. Basically, you have to optimize it in the lab. So you think about how we can change it. You can change something like this, a new tag, new level you can generate. This is the one thing. Clear, Bhavesh? Bhavesh?
Yes, sir. Yes, sir.
This is the number one. Now number two. Number two is this. See the surface modification. So here, how we modify the surface? See, avidin, biotin, right? So your antibody conjugated with biotin, and your surface modified with avidin, right? So in this case, because they are also some protein layer, so sometimes they can hinder the electron transfer on the surface. So how Bhavesh did, when he are going to do some experiment here, he changed the surface modification. So he used graphene oxide and some CS, means some another linker, some use like Tyrosine, something like they are helping to bind the graphene oxide on the surface. So this Tyrosine they used with the graphene oxide. So what's the new novelty things Bhavesh did? He basically increased the conductivity of the surface by using the graphene oxide. Also, because of the graphene oxide helps the actually much rougher surface. The number of the primary antibodies will be the high on the surface than the previous biosensor. So something like this way, you can increase the sensitivity of the sensor. So like this way, maybe you can design something new biosensor. You can get one new paper. So like this way, people actually generally doing their research. Actually, I am teaching you not only the theoretical knowledge, but also I am guiding you how to do your own project. When you will approach to your final year. So if someone publishes like this paper, so you can generate something new work by changing this step. Clear, guys?
Sir,
Tell me.
So if we want to compare, then we have to make sure that we are using the same sample. For suppose here you are using CEA kind of thing,
Yeah,
and
yeah.
earlier when you were using cardiac troponin I kind of thing.
Right.
So
Right.
so the actually our platform should be the, if we want to modify any biosensor, you are correct that we are taking into account this GS or graphene oxide and chitosan kind of thing. But
Yeah.
here both the sensors are quite different. We are not having the same.
Yeah. So your both sensors should be comparable, definitely.
Yes,
So if
sir.
you want to compare with previous sensor and your sensor, so basically what you have to do, you have to modify some surface with some, as I said, that's why maybe your senior done some work. So what you have to do, you have to borrow the concept and you have to check with your biosensor and compare. Definitely comparable means your target should be same, right? Then you just compare their data and your data. Now you can basically make a table in your paper. So this one already reported, but you done some work. So you can fix the target also. Like instead of changing the CEA, you can even use the PSA. Don't change the target. Just change the surface modification. Okay, now clear?
Yes, sir. Yes, sir. What I was saying earlier, this thing only.
Don't change the target. Instead, change the modification. Now we make it table. This one reported. This is the signal to background ratio. This one I have done, and this is the signal to background ratio. Clear? Okay. Any questions, guys?
Sir?
Anyone? Tell me.
Sir, quinonine is reduced to aminophenol, and T-shape is oxidized to its T-shape O kind of thing, and simultaneously the FC plus is changing to FC. So for this redox couple to work, the formal potential of aminophenol, quinoline, and T-shape O and FC should be similar. So what if that happen, if T-shape and T-shape is oxidized to T-shape O, and FC plus is changing or reduced to FC. So this middle thing that time will not work then. So how can we sure that this quinoline to aminophenol reduction reaction is working?
See, suppose this one. So instead of sodium boride, let's say it is T-shape. Okay.
Yes.
See, so first of things, it is very good questions. First of thing, so what do you have to do? So when you are going to use the starting material, so you know you are using FC plus, and you are using ANP, means you know that AP will form, right? On your surface, this one will form. You know this one. Now see, so what you have to do, you have to, you know that some potential you are going to apply, right? That potential you have to optimize. So first you have to take a cyclic voltammogram of your FC plus. Like this is already oxidized form, right? Higher oxidation state +3. So you have to take a cyclic voltammogram, first reduction and then oxidation, right? So you have to start from reduction, not from the from left side. You have to start from the right hand side, right? Is it clear?
Yes, sir.
When you are using the higher oxidation state and you are going to use some cyclic voltammetry, you have to start from reduction. I mean, because it is already iron third state. So you have to start from reduction, right to left, and then this. Then you will get some oxidation or your oxidation reduction potential where it is oxidizing, where it is reducing. Now, AP. Now you have to check where, because you know that from the ANP, AP will form on the surface, right? So you have to check another cyclic voltammogram for AP. So maybe AP can be oxidized here. Okay, so AP can be oxidized here. Okay, now, so it is, I know that AP is oxidizing here. That's why I put CV like this. So you have to get some chemical like AP and FC plus, and your first work will be collect the cyclic voltammogram. So this is for FC and this is for AP. So now you have to think about which potential you have to apply the finally, because at that potential, so they should at least show high contribution. I mean, this redox cycling. So you can see here, FC can oxidize around this potential and AP can oxidize around this potential. So that's why it is better if you can apply some common potential so that they can together can be oxidized easily. So it is better, that's why, to optimize the as I told you last time, that you have to optimize the applied potential. It is very crucial part of a biosensor. You have to potential application, how much you are going to apply, that you have to, mean signal to background ratio you have to check. So you know what is the signal, what is the background, right? So in this case, you can add FC plus NP and NaBH4. Okay, FC plus NP plus NaBH4. So this mixture you can use as a background substrate. Okay, and FC plus AP and plus NaBH4, you can use this one as a signal substrate. Clear? Right?
Yes.
So this,
Yes.
so this is your background substrate, this is your signal substrate. So no need to modify the surface from the beginning. Just on the bare surface you can try. Means you want to optimize the which potential you are going to apply. So you know, if you have target, AP will form. So let's skip it. So we will modify the surface with antigen antibody later on. So first take a bare surface. Like bare means no antibody antigen on your surface. So what you can do, you can take number 1 this, number 2 this. So now you have to apply this potential window within this, like from here to here. So 1, 2, 3, 4, 5 potential you have to choose. You can choose few potential. Now collect. Like if you want to apply like chronocoulometry, right? Then get chronocoulometry for background substrate like this reagent, and signal reagent this one, and get signal current. Suppose this one for like 0.2 volt. Okay, this is for 0.2 volt. So 0. Right? Okay, Rutin, clear?
Yes, sir. Yes, sir.
So same thing way, you have to, with this and this chemical, you have to check 0.3 volt, 0.4 volt, 0.5 volt, 0.6 volt. Like this way, you have to collect all the signal to background ratio. So you can find, when from this, from my experience, I can say around this potential you can get highest signal to background ratio. Because they both are clearly they can oxidize. So like
So
this
sir,
way,
that means
tell me.
so that means we don't need to optimize the aminophenol T-shape
No.
redox couple.
No, that aminophenol T-shape concentration also you can optimize. Got it?
No, sir, I'm talking about potential.
Oh, no, potential no need to. You can just check the cyclic voltammetry, which potential they are oxidizing. You will get some rough idea. So then, if you then you have to apply which potential you are going to optimize. You can see that they are oxidizing this area and they are aminophenol oxidizing this area. And within this area, you can choose 4 or 5 potential. Then you can get signal to background ratio. And you are right. No need to check individually FC and AP. Just mixture. In the mixture solution, you can get signal to background ratio. Clear, Pratin?
No, sir. Actually,
Tell me. I can repeat again. Tell me.
So that means we have to optimize the aminophenol FC redox couple first, one thing, and aminophenol T-shape redox couple. So based on that,
no, T-shape is
we
not
have,
T-shape just a reducing agent outside you are applying.
So T-shape will gets oxidized every time.
T-shape, yeah, that's why. Yeah, that's very good question. T-shape actually we have to use like 5 millimolar or 10 millimolar, very high concentration, because it will get always oxidized. It will not go back. As I said, that's why this, you can see the arrow, you're not coming back. So only this cycle, as they are cyclically, they are producing on the surface. But T-shape, they will always oxidize and it will not come back again.
So if T-shape itself get oxidized and it reduce the Fc plus to Fc.
Yeah, T-shape can reduce the Fc plus to Fc. But if it can reduce, then you will get the high background and you have the the very high side reaction. That is not
Yes.
good for your ultrasonic biosensor. Basically, your background will be very high. If that's why, actually, it is you have to prove that Fc. Actually, I know because I already developed this sensor that Fc plus and T-shape they are not reacting very fast. They cannot reduce very fast. They are reacting but very slow, very slow. So this reaction should be very slow. Otherwise, you will get the side, because of side reaction. You will get the high background. Clear?
Okay. Okay. Yes. Yes. Thank you, sir.
That is very good question you asked. Yeah, that is very nice. If this one react, then see, because of application applied potential, you are getting the electron, right? So that should be done by this reaction. But if sodium borate itself can reduce Fc plus to Fc, then this is basically your side reaction, not coming from your target kind. Not from the biosensor reaction, right?
Yes,
So then
yes.
you will get the high background. So this reaction should be minimized. So this reaction should be slow. So you have to choose such kind of chemical so that this one and this one should react slow.
Okay. Okay, sir.
Clear?
Yes, sir.
Yeah. And this is also very important that I mentioned, that your background substrate and this is your signal substrate you have to choose. And that within this solution 2 mixture, now you have to optimize the applied potential. Like different potential you can apply, and you have to collect signal to background ratio, like number 1 signal, number 2, number 3, number 4. Then you have to get which signal to background ratio is the highest one. Okay. Clear, guys? Everyone?
Sir.
Yes, sir.
Hello.
Yeah. Hello. Hello.
Sir, in that particularly ALP case.
Yeah. Tell me. Particularly.
Sir, in that ALP case, sir, will not that ALP means enzyme will react, will catalyze any reactions, especially in the markers, or means the sample we are putting will not give any signal or background in that particular case.
Yeah. So this ALP should not react with other case. Generally, ALP is the very specific enzyme. They only react APP. So if you have the APP, then only it will react, because it is very specific. Yeah, it is. You are correct. It should not react with other things. Otherwise, you will get the background again. So which cause background? Background means instead of if you are getting any current, instead of formation any biosensor, this complete biosensor, if you are getting any side reaction, this is kind of side reaction. We are saying side reaction. So this kind of side reaction can cause high background. Like just both in this described. So like T-shape should not react like ruthenium 3+ or Fc+, or ALP should not react with other things. So it should react only these things. Then only you will get high signal to background ratio. If there is any side reaction, they can cause high background. Clear?
Yes, sir. So means ALP is very specific for the APP only. It will not react, or it will not catalyze any other reactions.
Not react any other catalyzing. Right. So yeah, that's the things. When you will design any biosensor, like this is the engine, it's a biological thing. So it is like God gifted, right? Like somebody, like it is already natural thing. It will not react. But if you think about some artificial, like the Fe3O4 ANP, the same your question is applicable. So NP only should react with this, with not other things. So if somehow any other things, like you are going to use some like blood sample. So if you're in the blood sample is some species, that is called the interfering species, right? So if they react with this moiety, I mean this complex, then you will get the side reaction, then you will get high background. Clear? Okay.
Yes, sir.
Yeah, see again, okay, these biosensors are done. Then one more new biosensor. Here actually we use not antibody, here we use some DNA kind of thing. So instead of using the antibody, you can use the DNA, that is called a captured DNA. And on the surface, actually, see, you can see we use some gold nanoparticle, see, and we use some WO3-Gr. This is some composite, some tungsten kind of thing, some oxide and graphene, some composite we can use. So that is the things I'm going to tell you. We can modify the surface some different way. So we can use some nanoparticle like gold, or some metal oxide. See, some metal oxide, some graphene, like different kind of nanomaterial you can use together. Sometimes we are using only one single gold nanoparticle or only graphene oxide, or sometimes you can make a mixture of nanomaterial, gold, graphene oxide, carbon nanotube, or something like this. You can make a mixture and you can apply them on the surface. And let's check the signal to background ratio. So this is another kind of research that people are doing. How we can modify the surface a unique way, and we can get high signal to background ratio. And in this case, actually we use some, like, this is the DNA biosensor. Actually we use some capture probe DNA and some detection probe. Detection probe means instead of using detection antibody, like detection DNA we can use. And if you have target DNA, it will bind with your captured DNA, and I mean like a target. And you can use a detection probe, means like detection DNA that is already conjugated with some ALP, and ALP can be conjugated on the antibody, with the DNA with some like avidin biotin method. See here, APP here on another substrate with reaction with ALP, they can generate some species like AA. And this one can react with the FC plus, and like the same reaction we are using. So what change we done here? Just the surface modification. And you can use for the DNA detection. So this is for DNA detection. How? Because instead of using the antibody, we are using DNA here. Everything can be same or similar. Clear?
Yes, sir.
And
Sir,
yeah.
so like in case of TCEF or NaBH4, since you said that both of them get exhausted, so it may lead to decrease in the current, right? So if NaBH4 gets exhausted, then quinonine will not get reduced to aminophenol again.
Yeah,
so
that's why.
this will stop the reaction.
It's nice question. This one also. See, just I mentioned that. So T-shape. See, this one FC. This one. This is another optimize. See, for the optimizations is a very crucial part for development of biosensor. Optimization means what kind of optimization? So first you have to choose your material that I told. Second thing, you have to choose what kind of chemical you are going to use. When this is finalized, then you have to choose that, you have to optimize the concentration of the chemical.
Hello, sir.
Very much important. Yeah, tell me.
The screen is stuck, sir. I think.
Stuck. Is it okay now? No? Stuck?
Yes, it's stuck actually.
Okay, let's wait. I think then I can stop sharing and I can use again, right? Maybe some is possible. I'm sharing again. Can you see my slide now?
Sir.
Is it okay?
Yes, sir.
Yes.
Yes.
Yes, sir.
Good.
Yes, sir.
See, optimization of concentration of cells. see, so first things, a potential optimization. Potential optimization. Potential means what kind of potential you're going to apply. Then concentration of starting chemical that you are going to use, that you have to optimize. Okay, so FC plus, generally this one we are using very low concentration, around micromolar or millimolar, but millimolar means also like 1 millimolar, not more than this. So very low concentration we are going to use, because they are such kind of a catalyst, no need to use the high concentration. If you use very high concentration, so in that case maybe your background current can be increased. So generally this kind of redox coupled we are using very low concentration, and then that you have to optimize, like 1 micromolar, 10 micromolar, or 100 micromolar, or 1 millimolar. So like this way you have to choose different concentration, you have to optimize which concentration is the best one. So how you will choose that, I said the same way. So you have to make two solution. One is the background solution, one is the single signal solution. So what is the background solution here? Background solution here, FC plus, tell me, FC plus and OTP
And
tell me,
TSEP.
and TSEP. So this is your background solution. And signal solution, tell me, signal solution, which one?
FC
Plus, FC plus, not FC, FC plus.
Plus AA plus TSEP.
AA plus TSEP, right? So you have to collect some, you have to buy some AA and you have to mix it. Now by these two solution mixture, so first you can optimize the potential. Second, you have to optimize the concentration. So how you can optimize the concentration? You can fix one concentration, you can change the another one. It takes a long time basically, like permutation combination. Many experiments you have to continue, you have to carry out. See, so what you have to do, like how many chemical you have? 3 chemical, right? FC, AA, TSEP. 1, 2, 3, right? So what I would do, so like AA, you can fix these two concentration. Like you can use 1 millimolar, and TSEP, suppose, as I said, TSEP actually you have to use the high concentration as it will be consumed slowly. So to minimize the reaction, otherwise reaction rate will be slow, that you are correct. So that's why TSEP concentration should be very high. So generally we are using almost around 10 millimolar. It is a very high concentration. So within like few minutes, this 10 millimolar concentration will not be consumed. That's why we have to use the high concentration of the reducing agent. Other one, like AA you can fixed, TSEP you can use 10 millimolar fixed, and FC just change 1 micromolar, 10 micromolar, 100 micromolar, 1 millimolar, like this way, change. Okay, then you have to correct signal to background ratio. You have signal solution, you have background solution. Now maybe you get something like 1 micromolar case, you are getting highest one, then fixed it, remove other one. Now change the AA concentration, 1 millimolar, 100 micromolar, 10 micromolar, 1 micromolar. And so your FC concentration fixed, TSEP concentration fixed, changing the AA concentration. So like this, remember you got 100 micromolar is the best one. Okay, so now you choose the 100 micromolar is the highest one. So like this way, fixed one, fixed two, and change the other one. Like this way, you have to optimize which concentration is the best one, best concentration. And always just keep in mind, this kind of ECC redox cycling case, this reduction reagent concentration should be very high. Now clear?
Yes, sir.
Okay, so see, like this way, you are actually getting getting trained from my side how actual experiment can be done in the lab. Okay, clear?
Yes. Yes, sir.
Okay. Now I think this biosensor I already taught you. See, if I tell you that I already developed this biosensor, can you change it? Can you develop something new? Yes, you can do it something new. How? You can change this mediator. This is the very vital point, mediator, because they are actually determining how fast the electron can go. This is a catalyst. So you can change it. ruthenium to osmium compound, or FC, ferrocene compound, or something else, like cobalt based compound. And you can change, you can check the signal to background ratio, and you can design some new biosensor. You can change this one, and you can develop some new biosensor. And surface modification that I already taught you, 2-3 biosensor I have told you that we can design biosensor by changing the composition of nanomaterial on the sensor surface. Okay. See here, some other chemical I'm going to tell you. Tyrosine. So this is the tyrosine is the another enzyme. So you can use some, basically you can use some different enzyme, phenol. So it is specifically can oxidize and can form the catechol. So then it can be oxidized on the surface, and that can be reduced by NADH. This is basically a reducing agent. So I'm telling you some new reagent here, basically nothing. Otherwise the the principle is same. So what is the redox cycling name here? Can you tell me what is the redox cycling reaction here going on the surface? This is electrochemical.
EC.
And here is the chemical. Right? So this is the EC reaction. Okay, done. Now, something new here. See, instead of sometimes you can say, why we are going to use so many chemicals? Let's minimize the chemical, right? This kind of question, I think, it should come in your mind. So if you, when I am going, because after a few class I am going to teach you the now device development. This is the sensor surface development. Now I am teaching. Now finally I will come to the device development. Portable device, right? Some portable device will develop by using some microfluidic, some fabrication method, something like this. So if you are going to use some 3 chemical, so you have to make 3 channel, right? Something like some 3 channel, so it should come together to a sensor surface. Then you have to add it to a electrochemical workstation, to a portable workstation, right? So instead of using many chemicals, sometime we can avoid using chemical by designing our device some new way. This is called interdigited array. This is interdigited array, IDA. You can see, like this is a solution here. This compartment is the solution compartment. You can see your sensor developments. Here actually you have the solution, and this is one solid surface. This is an electrode, number 1 electrode and number 2 electrodes. You can see 2 electrodes we can use side by side, and in the tunnel in between we can develop the sensor. Are you getting my point here? Actually I will describe, but if you watch this one, if you see this sensor development, are you getting my point what I am going to teach you, guys? No?
No, sir.
No, right? Okay, see. Let's go back here. So here actually what I see. So you, in this case, so here you are applying some oxidation potential, right? So electron will be released, and that then FC0 will be oxidized to FC plus. So FC plus should be reduced to FC, then only this cycling will be completed, right? So for that we need some other chemical. So this chemical helping actually basically to reduce this FC plus to FC0. So if we can design a compartment of the electrode, so if we can apply here positive potential and here negative potential, see? So positive means you are, so actually it is the, so here actually this is the electron, it is the negative potential here. This is negative, this is reduction. This electrode surface is the reduction, negative potential. And here actually in this electrode surface, you can see the electron releasing, right? Electron releasing, it means this is the oxidation. So here positive potential you are applying, like plus 0.3 volt you are applying, here like minus 0.3 volt you are applying. Okay, so you can develop like 2 electrode surface, and in between So here, like ITO means, so here actually you put some indium tin oxide coated electrode, some electrode. So on that surface, you are actually, you can put some, you can say the FC. FC means instead of using FC in the solution, you can use the FC on the surface also. Means, as I say, the ruthenium hexamine or FC you can use in the solution, right? But this kind of compound, if you see the structure FC, what is the structure FC? I already taught you, right? Structure of the FC. Yeah, so this kind of phase, right? This one. So we can put here some carboxylic group by chemical modification. So this FC plus we can immobilize on the sensor surface also. That also possible. Because one end we can modify chemically carboxylic group or even amine group. So that one we can modify on the sensor surface. Like see, FC is there in the solution. So no need to add the chemical from the outside. It is on the surface attached.
So here it should be FC plus or FC.
See, as I said, the starting material is the FC plus, so it should be FC plus then.
Yes, sir. That's what I was saying.
If your starting material FC plus, then this one. But if you want your starting material FC0, then you have to modify FC0. Okay, that depends on your starting material. Now see, now you are using, in this case, you are using actually, you can see like say, if you use the FC plus, then FC plus will react with the aminophenol, right? Then your see here actually we are modifying. See in the right hand side you can see the biosensor, this one. So ALP already conjugated the secondary antibody and APP reacting and form the AP. See, right? So this AP will react with FC plus and will form quinonimine. This one. And see, generally we are using some, so that oxidation actually happened on this surface. And we are generally reducing this quinonimine. This quinonimine generally we are reducing by T shape. But that can be done by applying some negative potential. So if you apply some negative potential, that quinonimine can be reduced to aminophenol. So instead of using the, no need to use this kind of T shape. So you can apply some negative potential. So if you want to apply some negative potential, you can design some electrode where you can apply some negative potential, and that will help quinonimine to aminophenol. That can help. Clear, guys, or I should repeat? Hello, guys, is it clear why we are using the 2 electrode interdigited array here? Because one electrode actually here where we are applying positive potential, and that electrode actually it is oxidizing, and another electrode we are reducing the chemical. And in this case, ferrocene actually helping this to transfer the electron, basically as a mediator. As a mediator, it is helping. Or even one thing you can do here, maybe no need to use the ferrocene. Ferrocene you can remove. Just apply the negative potential. Then quinonimine can be reduced to aminophenol. Clear, guys?
Yes, sir. But if FC is on both the sides, then both of the plates should act as reduction.
Yeah, I think it is better don't use the
FC. Then we can, from one side we can apply oxidation and the other side we can apply reduction.
Right. So please remove this FC from here. You can remove the FC from here. Just apply the negative potential. Then you can complete the cycle. Right. So I think in this plate, no need to use the iron. Only one plate you can use the FC plus. Now clear? Okay.
So in the left hand side, how is this bottom plate accepting the electron?
in the left hand side.
Yes, sir. So just beside that FC part. So
Here,
it's
left
no, sir.
here.
Sir, right side of that FC. Sir, it's accepting electron from that quinine.
So quinonimine, see Fc plus. So when you apply the oxidation potential, so in this case, see aminophenol reacting with the Fc plus, right, and producing Fc0, right, right, and quinonimine is forming, and that quinonimine can be reduced on this electrode surface. I think so. One thing you can do, so I can simplify this one. I think there is so many reaction I drawn here, right? It is better I will simplify this slide. What you can do, because my goal here in this slide, I want to teach you how we can use the electrode for the in the redox cycling reaction. We can use the electrode itself, can take part in the redox cycling reaction. It is better I can remove this part, left hand side part. So I can make it simplified one. So let's remove this negative side, left hand side. Just think about the right hand side only. So, and also I will remove this Fc from the surface, from the bottom one. So actually here what I am going to show you, that if we apply some negative potential, so it can be reduced. No need to use the T-shape or sodium borohydride in this biosensor. So electrode itself can help you to form this ECC redox cycling. Now clear? Now clear, guys? Hello?
Yes, sir. But if we use FC, then on the bottom electrode, we have to use FC plus, and in the upper electrode, we have to use FC for the for oxidation to happen, and in the bottom for reduction to happen, right?
Yeah, that's what I'm saying. So you can think about, maybe you can use the FC or FC plus, or you can design like this way your electrode, so that basically you are minimizing the adding the chemical. This is my my goal to teach you in this slide. So next time I will simplify this one. There is, because there is so many reactions here, it is confusing. I wanted to teach you here how we can simplify our biosensor instead of adding many chemicals. So one thing you can remember, so we can immobilize some mediator itself on the electrode surface, like ferrocene, as I said, because you can see the ferrocene structure, then we can add some carboxylic group, something like this, and by EDC NHS reaction, this carboxylic acid group can be immobilized on the surface. So instead of adding from outside, we can immobilize the electrode mediator on the surface. Make it clear fast. This is very simple method, and no need to add the chemical from outside. One thing. Second thing, we can use electrode itself for like the oxidation reduction case. No, we can avoid the using some reducing agent, maybe like T-shape or sodium borohydride. So one electrode can be used for oxidation, another electrode used for the reduction. Now clear? Now clear, guys? Hello? Clear, right? Clear, right?
Yes, sir. Yes, sir.
Yeah, this is a very simple thing. Just see,
Yes, sir.
I taught you so many design. Just think out by yourself. I will recommend you, please search Google that how people actually modifying the sensor surface. You will get lots of paper, lots of journal paper. I can share you next class also, but or in between, I can share you some link in this Microsoft team. You can go that kind of journal paper. You can search like electrochemical biosensor surface modification or electrochemical chemical redox cycling, something like this. You can search. You will get lots of surface modification procedure. So basically, I am giving you some example, but you will get lots of example. So that's why I will arrange one presentation for all of you. So you have to prepare few slides and you have to present. So basically, it will improve your presentation skill also, and as well as this is kind of the assessment for you. So you have to present one biosensor work within 5 to 10 minutes. I will give you the time limit. just I wanted to see the main principle, not all the paper. You can read the paper. Okay, yeah, tell me.
Is it team or single, sir? Individual or team? The presentations you are requesting are team or individual?
No, it will be the individual presentation. Means that's why, because you are just so many students here, right? So in this case, maybe 1 week I can take, like, that's why I'm planning 5 minutes, because it is kind of, I wanted to improve your presentation skill. So if we make it a team wise, so it is difficult. So maybe 5 minutes to each. Maybe 1 week I can take like 10 or like 15 students. And then
Sir, or else you can do in pairs, like 2 people at least, 2.5 minutes, 2.5 minutes, like.
but 2.5 minutes is very less. It's difficult to present one whole paper. So 5 minutes is, I think 5 minutes is not enough, but 5 minutes is okay to present the principle only. Just principle. Not the whole paper, just principle. You have to read the whole paper and present within 5 minutes. And I wanted to see how you are presenting. So that I will let you know, not immediately, later. Maybe after 1 or 2 weeks later, I will tell you. Not now.
Before that, there will be MCQ type test, and after onwards, then the presentation of.
Yeah, I will arrange some MCQ type test also, because maybe end of this February or first week of March, I will arrange one MCQ type test also. That I will update you slowly. Okay. Okay, that's all for today. I'm taking your attendance. Yeah, tell me.
So, MCQ test will be conducted this month.
Your voice breaking. Tell me.
Hello, sir. MCQ test will be in this month, sir.
Bhuti, your voice too much breaking. I can't get you.
So he is asking that the MCQ test will take place this week, or this by the end of this February, or in the next month.
I think today is 22, right? Let's check in the March first week. Okay.
Okay, sir. Okay, sir. Thank you, sir.
Okay, so if you have any question, you can ask. Otherwise, I think that's all for today. And thank you. And if you don't understand anything, please ask me. Always I'm telling, ask me. It is not like this. Don't feel that I will feel bad. So always ask. I can clarify. So that's all for today. You can leave. If you have any question, you can stay. Otherwise, you can leave. Thank you and good night, all of you.
Sir,
Thank you, sir. Good night, sir.
Thank you, sir.
Thank you.
Sir, do you take attendance?
Tell me. Hello.
Sir, have you taken the attendance, sir?
Yeah, I took the attendance. I took.
Okay, sir. Thank you, sir.
Thank you, sir.
Thank you very much.
Thank you.
Thank you, sir.
Thank you, sir.